All right, so let's look at surface integrals. And so let's first talk about finding surface area, right? Okay, of some surface S. So the first step in that is we need to find parametrization for the surface. Okay. So let's just call this R of U and V. So you need, it's a surface, so you're going to need two parameters to parametrize this two-dimensional surface. Okay. So once you find this parametrization, the idea is to imagine that you keep one variable fixed and you change the other variable. So you want to find a tangent line, right? So like suppose that this is U naught, V naught, and you fix V naught, right? And you let U vary. So that way what you get is a path on that surface. And so if you differentiate this parametrization with respect to just U, what you get is a tangent vector. Yes. Okay. And if, on the other hand, you fix U and you let V vary instead, you get another path on that surface, and you can now differentiate that R with respect to V to get a tangent vector to that path and therefore the surface. And then these two vectors, as long as they're not parallel, right, we'll define a parallelogram, and that parallelogram has an area. Okay, so the area of that parallelogram would be given by the magnitude of this cross product of U and of these two tangent vectors. Now the cross product itself, so I guess I kind of drew that incorrectly, but that's okay. So this would be RV cross RU. Is going to be a vector that's normal to the that's normal to the surface. But the magnitude of that cross product gives you the area of this parallelogram. So it turns out that the surface area, differential surface area, is the area of the parallelogram times du dv. Okay. So this is going to be a fundamental formula. The differential surface area element, if you have a parametrization for that surface, is you differentiate the parametrization with respect to U and V, take the cross product, and the magnitude times du dv gives you the differential area element. Therefore, the area of that surface is the double integral over that surface of ds, which is, once you have the parametrization, it's just the magnitude of that cross product. Okay. So I'm sure you've seen the example of the surface area of a sphere, but let's look at the surface area of the sphere inside a cone. Okay. So the first thing we want is a parametrization of our surface. Now, the surface is a sphere. Okay, so what's the standard parametrization? What's a good parametrization of that sphere? Well, I mean, we have many options, right? We could parametrize in terms of x and y. X, y, and then z would have to be, let's solve for z, and the z would be positive square root of 1 minus x squared minus y squared. Okay, so that's definitely a legitimate parametrization. And if you wanted to find the surface area of that the sphere, a part of the sphere at least, you would have to find the cross product, where you first differentiate with respect to x, so the derivative of the first component with respect to x, derivative of the second component with respect to x, and the third one, that would be negative x over square root. And then you differentiate r with respect to y, so 0, y, and by symmetry, this would be similar. Okay, and you take the cross product. So let's see. The x component, this product minus that product. Okay, and then I guess that product minus that one. And finally, this minus that, so 1 minus 0. Okay, and then you would, to find the differential area element on that surface of our sphere, find the magnitude of the cross product, then dy dx, say. All right, so you would take the square root, and then you sum the squares of those components. Plus 1 squared. Yeah, I can post it. Okay. And so then we can simplify this by using the common denominator, 1 minus x squared minus y squared. Okay. Which would reduce rather nicely, right? Because the x squares and the y squares all cancel out. Okay. And then you would have to figure out the bounds of integration. So now that we know we want the area of that surface, we know what we're integrating, ds, which we computed according to our parametrization. Okay, but what would the bounds be? Okay. Well, so we're not finding the surface area of the full sphere. Only part of the sphere that's inside this upper nave of the cone. 0 to pi? Well, these are rectangular coordinates you have to remember. So if you take your sphere, okay, and then you have your cone as well. Okay. The sphere and the cone will intersect along some circle. And so if your parameter space is just a portion of the xy plane, you'd want to project that circle project that circle onto the xy plane, and that would be your parameter space over which you're integrating. So what is that circle? Okay, well, notice that we're essentially looking for the circle, which is the intersection of the sphere and the cone, which I'll write as z squared equals to x squared plus y squared. So to see where these intersect, I could just replace z squared with x squared plus y squared. So that's going to be x squared plus y squared equals a half. So that's a circle of radius square root 1 over square root of 2. Circle over so. So in the xy plane, we have a circle of radius 1 over square root of 2. Okay. So if I did want to parametrize this in terms of x and y, x, let's say, would go from negative 1 over square root of 2 to positive 1 over square root of 2. And then y would go from the lower semicircle, where y would be the negative of half minus x squared, to the upper semicircle, where y would be positive root 1/2 minus x squared. And then we could integrate, I guess, even though that's not very convenient, right? More likely we would try to do this in polar coordinates, say. Okay. But in principle, I could do this parametrization and get this integral. Now, what would be the wiser choice of parametrization for our sphere, for our surface? Well, that would be, well, you could use cylindrical, or maybe spherical would be a wise choice. Okay, so let's do a parametrization instead using spherical coordinates. So parametrize our unit sphere using spherical coordinates. Well, in this case, you know that in general, x is rho sine phi cosine theta, but here it's a unit sphere, so rho is always equal to 1. So we wouldn't have, the rho would just be 1. Likewise, y is rho, which is 1, sine phi sine theta, and z would be rho, which is 1 times cosine phi. So what you have here is a parametrization of this unit sphere in terms of parameter phi and theta. And so you could find the differential area element along that sphere using this parametrization. So we need to find this cross product of these two derivatives. So derivative of r with respect to phi and then the derivative of r with respect to theta. Okay, so we take the cross product. So that would be sine squared phi cosine so that's sine squared phi sine. And finally, this product minus that product. So let's be careful here. So that's cosine sine phi and cosine squared of theta minus a negative, so plus sine cosine phi times sine squared of theta. So then this gives us, using Pythagorean trig identity on this, you can factor out a cosine sine phi. Okay. And then we finally have to find the magnitude of that cross product. Okay. So we need to find the magnitude so we would just square each of the components and add them up, square root. It's a little painful, but okay. All right, so looking at this, we can really realize we can factor out a sine to the 4 theta, phi rather, and then we would be left with, let me just write that parenthetically, you can factor out a sine to the power of 4 phi, and we're left with cosine squared plus sine squared of theta, so that's equal to 1. Okay. Then we just rewrite this term. But we can do the same thing again. This time we can factor out the factor sine squared. phi, and then we're left with sine squared phi plus cosine squared phi, which is again Pythagorean trig identity. That's just 1. Okay. So we get square root of sine squared, okay, which in general should be the absolute value of sine of phi. But remember that in spherical coordinates, phi, if you look at the xy plane z-axis, phi is the angle measured from the positive z-axis, and it's restricted to be between 0 for the positive z-axis, to pi over 2 to pi on the negative z-axis. And so sine is positive for those angles, so you can just drop the absolute value bars. All right, so all that work went into finding ds, the differential area element. So the magnitude of that cross product turned out to just be sine phi. So now we're ready. Well, okay, we have to find the bounds for our parameter space, right? So again, remember, we're looking for the area of the unit sphere that's inside, rather, the cone, where z equals square root of x squared plus y squared. So we're only covering this like the cap of the sphere, right? So we only want to find that area inside the cone. All right, to do so, we still need to let theta go all the way around to cover the whole. But what are the bounds for phi? So looking again at the sphere and cone and profile, it should be obvious that phi, the minimum value for phi is 0 as we start on the positive z-axis, and then phi increases till it hits the side of the cone, where it would achieve phi would achieve its maximum value. But what's the value there? Okay, so we might have to put some work into there. Well, I can almost think in terms of cylindrical coordinates, right? If you look at the graph, if you look at this function and you use polar coordinates, you would get that z is equal to the square root of r squared. So z is the absolute value of r. So at least for positive values of r, which they should be in cylindrical, you would get z equals r. So it's this like diagonal line, z equals r. So this should tell you that since the slope of this line is 1, this angle has to be 45 degrees. Right, so the maximum value of phi would be 45 degrees, or I should say in radians, that's going to be pi over 4. Okay, so that's our parameter space. Okay, so now that we have our differential area element, we have the bounds for our parameter space or for our integral, we're ready to do the actual integration. All right, so let's do it. The area of our sphere inside the cone the integral over our surface ds. And so the ds turned out to be sine phi d phi d theta. And the bounds of integration for theta from 0 to 2 pi, and for phi from 0 to pi over 4. Okay, so now we can do that integral. With respect to phi, sine of phi is minus cosine phi for the antiderivative. All right, at the upper bound, we get this, and at the lower bound, we get, oh, wait a minute. Oh, minus a negative, sorry. So 1. Okay, that works. That's positive. Yeah. And then we get 2 pi from integration with respect to theta. Okay. So here I started off just with a parametrization which came naturally in terms of x and y. But then I realized that, okay, we're dealing with the surface area of a sphere, so I went to spherical coordinates instead with a fixed row of 1, since we have a unit sphere. And even though computing the differential area element took some work, it turned out to be nice. Okay. All right, so let's find the surface area of a cone. How to find the surface area of a tetrahedron. Okay, tetrahedron. I mean, you could use geometry, right? It's just a what do you call it? It's just a 3 simplex. But I'm thinking that you're not talking about how to find it using vectors. So if you have 3 vectors defining a tetrahedron, that would be 1/6 times the determinant. So 1 over 3 factorial times the determinant of the matrix you get, if you, or the absolute value, I should say. Okay. You're talking about how to find the, oh, that's the volume. Never mind. You want surface area. Never mind. This is volume. You want surface area. Yeah, integrals for the surface area. All right. Well, let's try not being general at first. Let's just instead define a tetrahedron in the first octant of space. Okay. So this is going to be a tetrahedron defined by this plane, but in the first octant of space, meaning that x, y, and z are all positive. And then we have our plane cutting through the first octant of space, and the x and y intercepts are 4. Sorry, x-intercept is 4, z-intercept is 4, and the y-intercept is 2. Okay, so that gives you a tetrahedron. Okay. Now, so this tetrahedron consists of 4 triangular faces. So we could set up integrals that would give you areas of the 3 sides that are in the coordinate planes, right? We could do that. But then, I mean, we can just use geometry there as well. Okay, so but the real challenge would be to find the area of the front-facing triangle. So that the triangle that's formed by the actual plane. Right, so I don't know how to describe that. It's just the front surface, right? The front face. So we can parametrize the surface. Okay. So we'll parametrize the surface, that plane, and there's a natural parametrization for this plane. So we want to parametrize the plane. Okay. So what's the natural parametrization for this plane? Well, since we can solve for one of the variables, say z, in terms of the other 2, the parameter space would be some region in the xy plane, say. X, Y, ooh, what is that? Times? Half times x times y? I don't see how that, maybe you meant plus, I don't know. But I would say that a natural parameterization, so let's just do this in terms of u and v. I would let x equal u, y be v, and then z has to be 4 minus u minus 2v. Okay. So then if you want the differential surface element, you would have to find this cross product of the derivative of r with respect to u and then v. Yeah, but the triangle isn't in, so if you try to use a formula for the area, you have to realize that we have a base area and base length, but you would still have to use some kind of geometry, which is not obvious, to find the height of the triangle, which we could do, right? We could definitely do geometry, but we want to use integrals. So I'm just going to parametrize that plane and find the differential surface element. All right. Now this isn't hard, right? Because we're going to see a connection to the normal to that plane, the vector 1, 2, 1. Okay. Yeah, that's the normal to the a normal to the plane. So differentiate r with respect to u, and then with respect to v. And take the cross product. So indeed, we just get the unit the normal to the plane, 1, 2, the vector 1, 2, 1. So if you take any point and you graph and you attach a vector 1, 2, 1 to any point on that plane, that would be a vector that's perpendicular to the plane. And then the magnitude of that is just square root of 6. Okay. So what that's telling us is that the differential area element on that front-facing triangle is square root of 6, so the magnitude of r, the magnitude here, times du dv. Okay. So if you want to find the area of that triangle, which is part of our the plane, then you would integrate the differential surface area element. And all we really have to do now, since we already found ds, is find the bounds for u and v. Not that you have to, right? Because your parameters essentially let x and y be u and v respectively. So the parameter space is just this triangle in the xy plane. Okay, so you're just integrating over that triangle. So you could parametrize it. That's not a problem. But you could also say that, okay, if I integrate du dv over that triangle, I would just get the area of that triangle. So that would be half base height, so that would be 4. Okay, so there you go. Now you could do similar kind of integrals for the other 3 sides that are part of the coordinate planes. I mean, that's not necessary, but the area of the surface area of the tetrahedral then would give you would be the area of the 3 sides in the coordinate plane. So that's going to be 4 plus 8 plus 4, and then plus the area of the front-facing triangle, which we discovered to be square root of 6 times 4. Okay. Okay. Now, to generalize this kind of procedure, like maybe we can try to find the area of a paraboloid, a basic paraboloid. So suppose that okay, paraboloid. So let's just do a basic one, right? Like z squared equals x squared plus y squared. Let's not get fancy. And let's suppose like z goes from 0 to 1. So to find the surface area of this object, we need to find a parametrization, and there are two obvious ones. Let's see what the difference would be. One is in terms of x and y, because one of the variables there, right, is already a function. Okay. But the problem is that if you parametrize in terms of x and y, your region of integration would be, if you project the circle into the xy plane, your region of integration would be a disk, right? So you might as well realize that I might as well go cylindrical. Yeah, exactly. Yeah, I think you meant cosine u, sine u, and v. Or something like that. Let's see. So I was thinking, let u be like the angle theta, right? So this is like theta. And v would be like r. Okay, so x would be, instead of r cosine theta, let's say we use v cosine of u, and y would be v sine u. But then notice that x squared plus y squared would just be v squared. Okay, so that's the parametrization I would use for our paraboloid. And we want to find surface area. So I would have to take the cross product of these two derivatives, du dv. Okay. So derivative of r with respect to u and then derivative of r with respect to v. Okay. And we take the cross product. So all right. Oh. Okay, so we can use employ the Pythagorean trig identity, and we're left with minus v over here. Okay. So then the magnitude of this cross product. All right. So let's see, this squared plus this squared plus that squared. Pythagorean trig identity for here. And then we can factor out a v. Okay. So let me just write that more clearly. That's a v. Perfect. All right, so now we have our differential area element. Now V is positive because it's like the radius, right? And the surface R is like the distance. I'm sorry, V is like the distance to the from the z-axis to the z-axis. So, all right, so there you go. And now we're ready to set up our integral. Let's see. All right. Using our parametrization, we get the area. Here's ds. Okay. So all right, so remember V is like R in polar and U is like theta. So the bounds for U have to be from 0 to 2 pi. I should have used R and theta, but I saw U and V in the chat, so there you go. So you have to go all the way around with respect to U to cover. And what are the bounds for V? Well, 0 to 1, right? Because you got the parameter space is just this disk. So, and that's a doable integral, so that should be 2 pi when you integrate with respect to U, and then when you integrate with respect to V, you're going to get 4V squared plus 1 to the 3/2 power, and then 1/12. Okay. This V goes from 0 to 1. So you get 5 to the power 3/2 minus 1. Okay. So pi over 6 times some constant, you know. All right. Now, there are other types of integrals, maybe called flux integrals sometimes. Where you'd integrate over some surface, but instead of but you can integrate a vector field, dot it with ds, which is a vector quantity. So for the previous integrals, right, ds was the magnitude of this cross product. Once you have a parametrization in terms of, say, U and V for formula's sake. Okay, but for this, you have a vector field, and you're kind of seeing how much, like, you have a vector field, and you want to know how much of this vector field, say, is flowing through some surface flux. ds represents a vector that's normal to the surface. Okay. And second of all, it has its magnitude would be like the differential area element on that surface. And the only part of the vector field that contributes to the flux of the surface is the part that's perpendicular to the surface. So that's why we have the dot product. So here, ds, we can show, or you've probably seen in class, is simply the cross product, right, without the magnitude, because that includes both the information about a unit normal, so a unit normal to the surface times the differential area element, where the unit normal would be the result of this cross product, but normalized. Okay. So, my bad. So as we saw before, this cross product is normal to the surface, and if you divide by its length, that gives you a unit normal to the surface. And then the differential surface element was the magnitude of the cross product times du dv. So the idea is that these cancel, right? And you're just left with this formula for ds, the differential vector surface area element. All right. So suppose you want to know the flux integral of this vector field through the side of a cone. Z equals square root of x squared plus y squared. Where we're gonna just limit z to be between 0 and 1, right? So flux of our vector field through the side of a cone. So at each point on this cone, we can draw our vector field okay. And we want to know how much of that vector field is flowing through our cone. So step one is we need a parametrization for that cone. And there's a natural one, of course, where we might, just like we did with a paraboloid, let x equal r cosine, let y equal r sine. So that way, if you plug that into here, you get that z would be equal to r. Right, and now we can just find this cross product where we probably want the normal to be outward pointing. So we'd want the unit normal to be, we should say, pointing away from the cone. So that might have to be specified here. So we can differentiate r with respect to, well, radius. So then with respect to theta. So this would, using Pythagorean trigon identity, we just get r. So does this? So this is going to be our. So ds, which is our unit normal times the differential surface area element along that cone. The way we have it right now, that has the wrong direction, right? Because we said the unit normal, we insisted, is going to be pointing away from the cone. So notice that for such a vector, the z component of the vector has to be negative, right? So that's okay. All we do is just, right, we have this cross product is inward pointing, but we wanted outward pointing, so we just take the negative of that. Just flip the direction. So you have to make sure your normal is pointing in the right direction. Okay. Now here we wouldn't find the magnitude because we're doing a flux integral, right? So next we would need to evaluate this vector field on the cone. So we're essentially composing the vector field with our parametrization for the surface, since we just want to evaluate the vector field on the surface, right? So here we would get x is equal to r cosine. Then we get y. And then we have z squared. So that's where z squared is, that would be r squared. Okay. And then we're ready to do our integral. Except that we don't have our bounds yet, but that should be simple enough in a second. Okay. All right, we have f evaluated on our surface according to the parametrization we used. Dot it with ds. Remember, ds is this cross product with the correct direction for the normal that we wanted, times dr d theta. So that cross product turned out to be okay. And I hope you see what the bounds are. Again, if you our parameter space is essentially the disk in the xy plane, and it's going to be a unit disk because z is the upper bound for z is 1. So if you have your cone and z happens to be 1, you get a circle of radius 1, and you project that onto the xy plane to get your domain of integration. Okay. So we get the dot product here, you get r squared times cosine squared plus r squared sine squared minus r cubed. And then it's pretty routine Pythagorean trig identity over here. You get 2 pi after integrating with respect to theta, and you get pi over 6 for the flux. All right, so we had an integral that was area. I forgot to. So that was just integral of ds. So if you had a parametrization, that was the magnitude of this cross product, du dv, and you had to find the bounds for u and v. And I forgot to do one when you have a scalar field. But then that would be just f composed with the parametrization times ds. So we might have to do an example, quick example of that. And then we had the flux kind of integral, where instead of ds, the differential area element, we use ds, the kind of differential area element times unit normal. So that differential area element times the unit normal just turned out to be the cross product here, du dv. Yeah. Oh, I don't know. I have no idea. I was gonna go, I think, through the week of. Well, when is Thanksgiving? So 27th. Probably. So yeah, next week will be the last one. That's right. I won't do it on Friday the 27th. All right. I'll see you next week then.